So, first question I ask when I begin my class to define welding. Okay, so what is welding? I want answers. Joining? What is joining? So definition should be self-explanatory, right? It shouldn't raise another question. Okay? Again, come on. What is welding? Come on, guys. So you are joining, right? So what do you mean by join? What is it? Come on. Yes, go ahead. Bonding? Okay, so bonding, right? What is bonding? Something happens, right? You have one metal and another metal, you have a time to join. What happens?
Formation of bonds.
Formation of bonds. Okay. How do you form a bond?
A metal fused to each other.
What is fusion?
Coalescence.
Hmm?
Coalescence.
Yeah, I heard some word coalescence. Okay. What is coalescence? Coalesce. What is coalesce? It's a mixing, right? So what is mixing? Right? Something is mixing to create a bond. Okay. So what is mixing? So you have one block and the other block, you want trying to mix it together, for example. So what happens? So you have one phase and the other phase, right? Okay. So you have interfaces. Two interfaces are there, right? What happens to the interface?
They become one.
It becomes one, right? How? Two interfaces become one interface. Something is moving. What is moving? Atoms are moving. Okay. Then atoms move. Okay. And then bond takes place, right? Okay. So if one atom moves from this place to other place, what do you call that? Yeah, diffusion in a metallurgical term. It is simple physical movement, isn't it? So it's a simple physical movement. And then if they interact, what will happen? They will also chemically interact. Okay. So if they physically move and chemically interact to create a bond, so that two interfaces become one interface. Okay. So now suppose if you want to now define welding, so how do you define? So it's a physical and chemical mixing of interfaces, right? It's a physical and chemical coalescence, right? So it's a physical and chemical coalescence of the interfaces, isn't it? So you are physically mixing as well as chemically interacting. So physical and chemical coalescence of the interfaces, so that you can two interface becomes one. So where is the driving force? Because you are reducing surface energy. Okay, so two interfaces becomes one interface. But can it happen without applying any external driving force? No, right? So then what do we do? Yeah, you need to apply heat or pressure. Very good. So we have all terms defined: physical, chemical, coalescence of interfaces. And do the interface coalesce themselves? No. Do they coalesce themselves? No, we need to apply some driving force so that they coalesce. So how you apply that, how you give the driving force? By giving some energy to the system, and the energy is given by heat or pressure or sometimes both, isn't it? So you apply either heat or pressure or sometimes you apply both, right? So we can define now the welding in classical terms is physical and chemical coalescence of interfaces by the application of heat and or pressure. Okay. So, this is the classical definition, because everything is covered. Definition should cover all the physical phenomena that are happening in a process, right. So, we have a physical coalescence as well as a chemical coalescence of the interfaces. And how do you make the coalescence happen? By application of heat or pressure or both, right. It is clear. So, this is the classical definition of welding. Okay. So, this definition, whenever someone joins my professor's group, the first question he asks is this, and how good you answer this question, based on this his teaching would be. So, I will also judge you by the definition, how you are able to tell, so that I can define my level of teaching. Okay, now I understood the level. Okay, okay, good. So, now we define the welding. Okay, so, you have now welding process defined, but then next question comes, why welding? Why do you weld? Why can't you join two parts by putting a bolt? Corrosion? Why corrosion free?
Because in lifting there is a cribite corrosion.
Yeah, so there is a dissimilar junction created when you use a mechanical connections, mechanical joints, right. So, that means that there is a potential difference. So, that is not good for corrosion point of view. The other advantage is weight reduction. If you use a mechanical connection, you are adding more material, right. So, the component weight increases. Okay. So, the weight reduction by welding is enormous. It is also homogeneous physical and chemical coalescence. So, there is no real sharp interface. So, corrosion problems are not there when you are doing welding. Similarly, you gain advantage of not using mechanical connections. You gain advantage in terms of weight saving as well. Okay. So, therefore, so welding is advantageous in engineering applications, because you avoid the sharp interfaces which can lead to corrosion or stress partitioning, okay, load partitioning. Okay. If you have a sharp interfaces, you have also a load partitioning, right. There is the stress will be acting on always the member which is weaker, right. So, you gain advantage of removing the sharp interface in mechanical connections, where the interface becomes smoother, relatively smoother, okay, and you gain the weight advantage. So, these are the main engineering advantages you gain by using welding, and the weld becomes stronger, I mean joint becomes much more stronger than mechanical connections because of the removal of the sharp interface. So, when you use mechanical joints, obviously the load will be distributing differently, right. Yeah, it is clear. So, there is the advantage of welding compared to the mechanical connections. Yes, it is clear. So, now having understood what is welding, why welding, we will go in deeper. So, right. So, we look at see what are the common welding processes that are available currently for engineering applications, and how we can classify them, right. We look at it. Okay. So, if you look at the common welding processes, we can classify into two, again that from the definition. So, definition says heat or pressure. So, we can classify the welding processes, those use heat to weld, and the welding processes those use pressure or load to weld. So, this is a very major classification. There are various classifications possible inside each processes and each methodology. So, generally the common classification is those use heat or fusion welding processes and the pressure welding processes. In both cases, for example, in fusion welding processes, you will also apply some cases pressure, but rate controlling heat, if the heat is rate controlling, so then it is commonly known as fusion welding processes, or if a load is rate controlling, then use a pressure welding process, right. It is clear. But again, this is not a real good classification, because I have been telling, right. So, we can either use heat or pressure, or sometimes we use both, where heat will be the rate controlling and the pressure will be assisting the coalescence, the process. Whereas in the other case the pressure is rate controlling, where heat is also used to ease the coalescence. Okay, so we can classify into broadly the processes into two major classifications, even if you use fusion or heat as an heat source mainly, or pressure, by in a way of making our joint. Okay, so suppose if you make a welding process where you have a liquid presence at the interface, so we call it as a fusion welding process. Okay. If the interface is not molten, interface after welding, if you see that if you make a bond in solid state, there is no liquid when you make a joint. Okay. There are a couple of exceptions, but in generalized rule is, so when a liquid is there at the interface, when you are joining that interface, so that is known as fusion welding process. So when you make a joint in solid state, there is no liquid. Liquid is pushed apart if the liquid is present, or there is no melting of the interface, right. So that is known as solid state welding process. Okay. And then further, based on the heat generation mechanism, we can sub-classify these two processes into various processes. Like for example, I would listed the fusion welding process. These are commonly used fusion welding process used for engineering applications. So based on the heat generation mechanism and how we change the process based on changing the consumable or changing the electrode or changing the gas, changing the atmosphere, or changing the heat source from arc to say plasma or laser or electron beam, or you generate heat just by resistance heating, you still have a liquid. So if liquid is there, we call that process a fusion welding process. Okay. So you can list all the processes that are available, like metal arc welding, gas metal arc welding, gas tungsten arc welding, submerged arc welding, laser beam, electron beam, resistance, electro-slag, malonothermic, oxy-gas. Okay. So these are all the processes where the interface melts. Okay. And if you move on to the solid state welding process, where there is no real melting of the interface, liquid does not really coalesce, only the solid unmolten regions coalesce. So for example, friction, and there are various variants of friction processes. Simple friction welding, where you have rotary friction, two rods are rotated against each other and then you generate heat, or linear friction. Okay. So linear friction welding, or friction stir, where you have a rod and then rotated against the interface. Okay. Or cold pressure, simple pressure welding. So you can apply simple pressure as well, and it works. So during my PhD times, so I had to supervise a laboratory for BTech students. So in that process, we wanted to make a simple backing plate, a simple plate, and we asked a student to mill it very nicely. Okay. And students somehow did it so perfectly. It's a heavy stainless steel block, and they brought it and put it on the welding table. You could never remove it. It's still there. If you have a perfect interface, okay, so if you have an extremely uniform interface, and if these two interfaces come into contact to each other, and if you apply a sufficient load, you can also make a cold pressure joining. So interface preparation, if it is really good, you end up making a joint. Okay, so that by applying a simple load. So cold pressure welding, okay, and diffusion bonding. Okay, some metallurgy involved in it. So you pass or you transfer atoms from one interface to interface by a gradient in the composition, which can drive the coalescence of the interface, right? So, that is a diffusion interface, and you can also use ultrasounds. So, ultrasounds can also locally deform the interface to coalesce. Okay, so, ultrasonic welding, and we also have nowadays a new process invented, and we are going to install in 2 to 3 months in our lab as well. That is magnetically impelled arc butt welding, where we have arc and the pressure. It is very difficult to define which is rate controlling in this process, whether arc is rate controlling or pressure is rate controlling. So, we left it hanging. Okay, so, in this diagram it is hanging because it uses both arc and the pressure. Okay, and we will come back to that now when we look at in detail. So, why it is hanging, but this process uses both arc and the pressure to make the interfaces coalesce, right. It is clear. So, this is the broad classification of welding process, and we are going to look at each process in detail in this course. So, starting from gas junction arc welding and gas metal arc welding. Okay, so, we will move on to the variants of gas metal arc welding, what are the advantages and what are the modifications that are made to make this process more efficient. Okay, and then we will move on to the resistance spot welding, resistance seam welding, projection welding. Okay, and then we will move to laser beam welding, electron beam welding, and then we look at some of the uncommon techniques like thermit or aluminothermic welding, okay, and oxy-gas welding, and so on and so forth, right. So, if you look at the modern development of the welding process, the invention of arc or the use of arc for the welding process, that happened somewhere in 1865 or so. Okay, so, the first weld when human being made a modern weld, not the archaeological weld. So, the first weld was made using resistance heating. Okay, so, someone accidentally welded 2 wires, copper wires. So, when he applied a current, there was a problem and they fused together because of the force. It made into one single wire. So, that was the reported first joining using a modern so called welding technology. And then the arc came into picture. The moment arc was controlled by a regulated power source, and then arc welding developments took place somewhere in 1890, and thereon there are various modifications carried out in arc welding process, right. It is clear. Okay, so we will move on to the detail, right. So, first chapter we will look at, I have mentioned arc. So, this is important. So, we will understand in the first chapter what is this arc, why is it important, right. The arc is there in nature as well, or the phenomena that is happening in arc, it is also happening in nature in various ways. Okay. Can you give me some example of natural arc or natural discharge? Lightning. Okay. What else? Yeah, spark. So, these are all naturally occurring, lightning for example. But can you use lightning for heat source? Why?
Uncertain temperature.
Cannot control.
It is momentary, it is not stable. Okay. So, you need to have a sustained discharge, right. So, then only you can use it. If it is momentary, spark is momentary, right. So, if you make it sustained, then you can use it, heat source. So, that is where trick lies. So, how do you make this discharge sustainable, right. That is what we can control the arc to use it for a non-welding application, right. It is clear. Good. The classification is clear, right. So, how we classify the welding process? So, we classify into 2 major, fusion welding process and pressure welding process. So, we may also apply pressure in fusion welding process and vice versa, but the rate controlling is either heat or pressure, and then based on the interface behavior, whether it is melting or not melting. So, we can further classify the welding processes into the fusion welding process or solid state welding process. In fusion welding processes, the heat source is different. We can use arc as a heat source. Even if you use the arc as a heat source, how you generate the arc, okay? And that can also vary, and based on that we can also further classify into various welding processes. So, and then we can also use a laser as a heat source, diffuse to melt the interface, or you can use electron beam, or you can also use resistance heating, or you can also use a simple gas combustion like in oxyacetylene or oxy-gas torch. Okay, so, we look at all the physics behind these processes, and then we will move on to the solid state process, right. We will move on to the arc welding process. So, that is the first chapter. Yeah. The first question again, I will start with the definition. So, if you are clear about definition, you are also clear about the concept. Let us define arc. So, what are the important parameters or the fundamental rate controlling factors you may expect in arc? What is it?
Potential difference.
Quite high potential difference. That means voltage is high. Wrong.
Electrons and ions.
Electrons and ions. Okay. Why do you need electrons and ions? Suppose if you have a conductor, okay, you pass a current from say this point to this point. It can travel, right? The electrons are charge carriers. They can be transported as long as you have a potential difference, right? So, how do you define the charge carrier? There must be unit, right? What is unit of this charge carrier?
Coulomb.
Coulomb. Good, very good. What is Coulomb? What is Coulomb? Yeah, you feel free. I am not going to scold you, right, if you say wrong answers. Something is moving, right? What is moving? Electrons are moving. Very good. So, what is the relationship between the electrons and coulombs? 1 coulomb is equal to 19, 18. Okay. So, at any point of time, number of coulombs define the amperage, right? The ampere we define coulombs per second. At any given time, so how much coulomb is there, that defines the charge carrier density, or unit of the charge carriers, coulombs per second, that amperage, right? So, if you pass say this much coulomb electrons or 1 coulomb or whatever over this conductor, and it kept at a potential difference, but the electrons would happily travel because there is a potential difference, because there is a conductor and through which these electrons can travel, right. So, I use the word potential difference, you also use the potential. What is the potential difference? How do you define, what is unit of potential difference? Volts. What is volt? Definition. When do you say 1 volt? There must be a definition, right? So, these are the basic things, basic definition you need to understand. Come on, go ahead. Some words, some terms you can give. You have defined coulomb, okay. So, if 1 coulomb travels over a potential difference in a second over a unit length, it is 1 ampere, right. So, what potential difference can give you 1 volt? Yes? So you need to think about energy. Electrons cannot travel by themselves, right? You need to, what is the driving force? What is the push? You need to do some work, right? Right? Or electrons to do work to move from one place to other place. How do you define that? Yeah, so if you want to attend my class, you need to spend some energy. Yeah? You are spending energy, you are burning energy, right? So what is unit of energy? Joules. Good. So now can you relate? Joules per second is what? Watt, right? So now you define volt. So when 1 coulomb of electron travel in a second over 1 meter, the work done is 1 joule. If the work done is 1 joule, then the potential difference is 1 volt. Okay, so in other words, if the potential difference is 1 volt, when 1 ampere current passes through that, it gains 1 joule of energy, right? Or if 1 ampere travels through a potential difference of 1 volt, the work done by the electron is 1 joule when 1 ampere current travels. So that is how we define the voltage and the amperage. Okay, so now we have a conductor which travels, which passes the electrons from one end to other end, which is kept at a potential difference. So now we break the conductor. Okay, there is one conductor here and other conductor here. Now you pass a current, okay, from this end to this end. Would the electrons travel from this interface to this interface, from here to here? Why? What happens? Air is an insulator. But if you want to still pass the electrons from here to here, what should you do? Placing one more conductor. I won't give you conductor, only air. More voltage? Decrease? Decrease the gap. If you make it close to each other. But even then, you will not expect current would be passing from one end to other end. More voltage. You apply a high energy or a lot of amperage, then what will happen? Yeah? Then what will happen? What will happen to this medium in between these two conductors? It will ionize. So what do you mean by ionized? What do you mean by ionized? So the atoms and molecules would lose electrons. By doing so, they become positive ions. In this process, you create more energy carriers, isn't it? The electrons and ions are the energy carriers, right? In a solid conductor, electrons are the only energy carriers. But if you have ions, you have both electrons and ions as energy carriers, right? So suppose if you supply enough energy in such a way that the electrons from here would interact with the medium, in that process you create more electrons, right? And if you create more electrons, obviously the gas atoms and gas molecules would become ionized, right? And this process is roughly known as, or there is a term controversy, but you can always say that if this happens when you create more ions, and this process is known as discharge, right? So, moment discharge happens, you generate more electrons and ions, and if you create more charge carriers in this medium, what will happen? These charge carriers can transfer from this interface to this interface, right? And this discharge can be various types of discharges. So, you see the lights over here, this is a type of discharge, right? Isn't it? Lightning is a type of discharge, right? Arc, it is also a type of discharge, right? The only thing is the amperage current and the voltage potential difference will be different in various discharges. For example, you have a gas discharge here, discharge in a gas, it is also known as glow discharge, where the what is voltage here? What is the potential difference between the two terminals? 230 volts in India, right? So, we use 230 volts. Amperage? Come on guys, you are engineers, right? So, what is the current amperage you use at home? Yes? 10, 15, 6, somewhere or there about amperage, okay? But in arc, we use different voltages in amperage, that is it, right? It is, the phenomena is the same, what you use it over here in glow discharge, it is same as happens in arc. We have generation of electrons and ions in a gas medium, but only thing is the current and voltages are different. So, if you look at the varying current and voltage, there are three types of discharges which are observed in a when a carrier passes through a gas medium, okay. So, the three discharges are known as the Townsend discharge, glow discharge and arc discharge, okay. And these are all stationary. If you look at the natural discharges like spark or lightning, they are momentary, not even a second, right? If lightning is sustained over a second, more than a second, then you have a problem. So, these are momentary, the spark and lightning. But if you turn the lights on, the glow discharge, as long as you have the energy, the glow discharge is sustained, isn't it? If you switch off the input charge carriers, then discharge also decays. So, you make it sustained, right. So, only thing is this difference between these discharges are the amount of current and voltage, right. So, we can define, if you want to define an arc, it is the sustained discharge of atoms and molecules between a potential difference. By doing so, the movement of electrons and ions are carried out, okay. So, it is a sustained electrical discharge in a gas, and due to this electrical discharge, what do you mean by discharge? Creation of the avalanche of ions and electrons. By doing so, we can conduct the energy, or the energy carriers can travel from one interface to other interface by the movement of the free electrons and ions, those are generated by this discharge, right. Is clear? So, there are three possible discharges, and we can classify based on the current and voltages, whether it is arc discharge, a glow discharge or Townsend discharge. You see the nature of the curve in three discharges. There is distinctive differences in the range. So, we have voltage can go up to 2000 volts and here a current up to 1000 amperes. If you look at this region where you have a high current and extremely low voltage, but if you look at the curve in these three regions, flat. So, that is the unique characteristics. If you want to make these discharges sustained or for longer time, if the curve is going like this, even for a small change in the amperage, you have a large difference in potential difference, or if you have a large small change in potential difference, the charge carriers, the amperage also changes, then you have unsustained discharge, and that is not sustainable, right. So, these guys, so in arc discharge and glow discharge and Townsend discharge, you see that the curve becomes flattens. So, even if you change the charge carrier density, the potential difference does not change much. That means that even if you pump up more current, the electrons they don't gain much energy, isn't it? That is the difference, right? That is the definition of volt. If you pump up the electrons, and electrons would start gaining the energy because of the change in potential difference, then you can't make it sustained. They will collide and then you will have maybe explosion, like. So, you can't sustain that discharge. So, if you want to sustain the discharge, even if you pump up current, the potential difference should not change. That means that these energy carriers should not gain much energy, then you can make it sustainable. So, if you look at these curves, you see that glow discharge, it happens in the voltages somewhere around the operational voltage. So, what we have about say 200 to 500 degrees 500 volts, where you have glow discharge, or you can also make it lower, but depending on the characteristics of the gas what you use. And generally, commonly you can see that the glow discharge can happen in the voltages somewhere in between say 200 to 500 or so, and the amperage the range of say 1 to 10 or 15, right. And we also have another discharge which is known as a dark discharge or a Townsend discharge, and that happens in natural ways, photovoltaic effect. Okay. So, it can happen for example, you have a cosmic ray falls on a gas medium and you generate some discharge, and if you have a very high voltages, so you may induce another discharge. Okay. So, that happens in every time when you have a high voltage system discharge. Okay. And welding, because we use arc, and which arc is struck between extremely low potential difference. You see that 10, not more than 20 volts. Okay. So, that is one of the major advantage of using arc, because system is operated at extremely low potential difference. So, that is why it is safe to use. When you touch something, if it is 230 volt, you feel. So, when you touch a circuit, if it is 10 volts, do you feel? You do not feel, right. So, that is what make the arc heat source is very attractive, because the system is operated in very low voltages, but the amperage can go up to as high as 1500, even close to 2000 amperes. So, you can operate it from say 10 amps to 1500, 2000 amps, you still there is no significant increasing in voltage, it will be only 10 to 20 volts. Okay. So, this discharge happens with a very high current and extremely low voltages, and low discharge happens in the voltages ranging from say 200 to 500, and the amperage will somewhere around say 1 to 10 amperage. In Townsend discharge happens extremely high voltages, okay, in very small amperage, 1 or 2 coulombs of energy carriers are generated. Okay, it's clear. So these are the common discharges which are used, and based on the amperage, the energy carrier, you generate energy, because in arc we have a high amount of current, so you can generate more heat. So we will look at in subsequent classes how these high energy carriers, electrons and ions, they interact and then they produce heat or energy. Okay, so it's, to summarize, the basic definition of the ampere volt governs the heat generation. Okay, so the ampere and the volt governs the heat generation, and if the energy carriers have to be transported from one interface to other interface, we need to have a discharge. Okay, so this discharge can happen so when you have an ionization of the medium which is there in between the conductors, and this ionization lead to generation of more amount of ions and electrons, and the movement of ions and electrons in a sustained way in a gas medium, okay, is known as arc. Okay, so in order to do that, so you need to have a sustained discharge. So you need to keep on generating the electrons and ions. Okay, I hope it's clear. So we'll finish this, and then we'll continue from next class. So any questions? So we looked at the definition of welding itself, to summarize, and then we move on to why welding, and then we classified welding processes based on the heat or pressure or based on the fusion or the solid state, and then we started looking at the very important the welding process, the arc welding process, and we defined what is arc. Okay, so we'll go even deeper in defining the arc. What are the discharge mechanisms, what is discharge, why discharge, and how heat is generated by this discharge, and what are the factors controlling the discharge. We look at all the physics. These are all high temperature plasma physics. Okay, so we'll see next class. Okay, we'll end up here. Okay, good, thanks.